after the statement of the Ax-Kochen-Ershov theorem, let me remind it. That K gamma K and L K L gamma L the valid fields. So there are 2 points of FP characteristic 0. Which means that both the field and the residue field are characteristic 0, and secondly, they are Henselian. So Henselian is, satisfying Hensel's lemma, the lift of roots of polynomials from the residue field to the field itself. And so if I have these 2 properties, then I have condition for the theory of the field. L gamma L, if and only if both the fields, the residue fields, have the same theory, and the value group as well. Okay, so what is this? This is in the language, in the 3-sorted language. Okay, so remember this symbol means that they satisfy the same sentences. Okay, those formulas only constructed from stratification and which don't have any free variables. So they have the same sentences if and only if those have the same sentence in the language of rings. Okay, I think we denote the language of rings in this sort and rest. It's language of rings, and this is in the language of ordered language of group, but it's ordered. Okay, let me just remind you this minus 0 the order and symbol, because I'm only talking about the groups here. Okay. Okay, so actually this depends every time I use this notation, it's relative to a certain language. Okay. This is relative to this language, this is relative to this one and to this one. Okay, so there should be one direction which is clear. It's that if this holds, because this one contains, for instance, the sentences that are true in K. So it means in particular that every sentence in the language of the residue fields, which is true here, it's true in here. So it's true in here, even only if it's true in here. So it's the same. So the hard direction is really going from right to left. And that's really what's behind this intuition of the valid field is essentially, in this context, determined up to its residue fields and its value group. Okay, so you remember the Ax-Kochen principle from yesterday, which said that if I have a sentence in the 3-sorted language, then given a sentence, there is only a finite number of primes such that QP and FP double bracket T disagree. So for every sentence, they agree for almost only sentence for almost all primes. So let's prove that using only this Ax-Kochen-Ershov theorem. proof of Ax-Kochen principle from AK. Okay, so let me remind you what it means. So for all theta L3S sentence, then QP of theta if and only if FP of double bracket P satisfies theta for all but finitely many primes P. Okay, so if this is not true, what does it mean? Let's assume that there exists a sentence. Assume that there exists a sentence so that this is not true. It means that they disagree on an infinite set. Assume not. Then there is a L3S formula such that for an infinite set of primes, call it S, we have that Q. Okay, so I'm really working in the three sorted language, but yeah, I didn't precise, but let me be more precise. So we have the field, the residue field, and the value group is Z, proves satisfies theta if and only and for instance FP of double bracket T and Z does not satisfy theta. Okay, for all we have for all P S this holds. Okay, and because it's a structure, it either satisfies this one or the negation. Okay, so it means that here this equivalent E of T FPZ satisfies not this and this equivalent. So the definition of truth doesn't mean anything, but
there you mean sentence. There's
yes, thank you. Yes, good. Sentence. Okay, so what do I do now? I take a Q in ultra filter on the set of primes such that S belongs to U. Okay, by the how it was called, probably the ultra filter lemma or something, can always extend a given set of subsets. So here I'm just taking the singleton S and using Thom's lemma that exists in ultra. It's an ultra filter on primes. It contains S. And now I look at KK, gamma K, the ultra product for P, like P in this ultra product of the QP, Z, and L, KL, gamma L to be the other ultra product along U of the FP etc. But P Z. Okay, so this time, contrary to the proof of the left principle, I take two ultra products. Okay, so let's first look at the first one. What's the characteristic of K? Let's go K, K, gamma K. What can you tell me about the characteristic of K? Okay, it takes the ultra product along all the P's of the QPs. Okay, so everyone is of characteristic 0. So all those sentences that say 1 plus 1 plus 1 is different from 0, they hold for all of them, because U contains the set of primes. By Walsh theorem, it's again of characteristic 0. Okay, is it clear? Okay, let me maybe remind you a little bit more. The set of P primes such that QP satisfies 1 plus 1 is non-zero. What is this set? Let's see. Okay. Let's say okay for all n. So it's all of them. QP is of characteristic 0. Okay, so this is really the set of primes. And the set of primes belongs to U. It contains the set, and the ultra filter is closed on the subset. Okay, so this belongs to U. So Walsh theorem tells me that 1 plus 1 plus 1 different 0 holds in the ultra product.
It's also a quotient of the product of the QP and the product of the QP. And have a quotient of it.
Right. Yeah, right. It's a ring homomorphism
from product of the QP to some quotient.
I guess you can say that too. Right. I guess you can. Yeah. Just for this case. Yes. Yeah. Okay. But for other sentences, then okay. But just as before, okay.
So the statement, can you remind us just for memory?
Yeah.
Walsh theorem.
Yes. So the ultra product, let's say, of I. Okay, it's not in U, but it's relative to some I of some structure, and I satisfies a certain sentence if and only if the set of I such that Mi satisfies this sentence is an element of my ultra field. This is, how is it? Walsh. Okay. Okay, so this is a characteristic zero. All of them are in it. What about, so here I'm really talking about the characteristic of K. What about the characteristic of the residue field?
Well, the algebra argument still says that it contains Q, right? So,
does it? No, but K is FP here.
no, but I'm saying, I see what they said. You're right.
I'm not sure it goes that way for the.
No,
I'm not sure you can tell anything about the.
I think you have to
image,
use it.
right?
No, I think you have to use it. Yeah.
So here for the same a similar reason. So now I'm looking at the set, let's say the set of primes, such that 1 plus 1 plus 1 in Fp. Now let's fix a prime number Q. The set of primes such that the sum Q times of 1 equals is different from 0. What is this set? In Fp, so P such that 1 plus 1 plus 1 Q times is different from 0. In Fp, what is this set?
That primes minus P.
Exactly. This is the primes without Q, right? And so this is a cofinite set, and we saw that non-principal filters, they always contain the spatial filter. So this sort of very, very big set, cofinite set, they also belong to the ultra filter. Which means that if I fix a Q, I know by Wolf's theorem that the ultra product of, okay, so KK, maybe I should make this precise, KK, really what's happening is that this is the ultra product of the P's, for all P's. Okay. For each Q, the set such that it is not of characteristic Q is big, so this field is not of characteristic Q. And this is for all Q. Okay, so not of characteristic. And so the characteristic of this is 0 or infinity. They used to say characteristic infinity in the old papers. Yes. Well, with this, it makes a lot of sense, I think. Anyway, it makes a lot of sense. Anyway, okay, so here, this is this so-called ultra pseudo-finite field, and it's of characteristic 0 because I'm taking along all the P's, and this also, right? Also characteristic 0. I'm doing the same thing. They have the same residual field. Okay, it's getting a bit messy. Let me clean this up.
But it is clear. Your characteristics.
Exactly. Okay, so this I will erase. Okay, so what did I check? I checked that K is of characteristic 0. K equals 0. Char of KK is 0. And by the remark from yesterday, V as a valid field is Henselian. Because I gave you the characterization of Henselian by being able to lift simple roots. And yeah, that was an exercise, I guess. Did you check that this was indeed first order expressible in the three-sorted language? Did you? Did you? Did you? It's in the notes. It's not a good reading. Okay. But yeah, okay, it's Henselian. Okay. So again, there is a sentence. There's a bunch of sentences. There's a bunch of sentences that say for each degree d, if I have 0 in the residue field, which is not a root of the prime of the derivative, then I can find a root such that the residue of this root is the same as the root I have in the first place in the residue field. You can say this for each d. And so for each d, you have a sentence saying that the roots of polynomials of degree d lift. And so because for every d, this field being Henselian will satisfy this sentence, and for every d, this one also will satisfy this. Okay, so KV is Henselian. Is it clear? You don't need to write this sentence? Yes.
Prove that U is non-traceable.
Okay, good question. You can, because S, I think that was in the lemma. If you take any S infinite, then you can, there exists a non-principal. Was it in the statement?
I mean, you can start with the Frechet's filter and then any. I mean, you can
and add it,
extension of
and add the set S. Yes. Yeah, right. S is not in the Frechet filter, so you can just take the Frechet filter, add S, and take an infer filter that contains this set.
Thank you.
It might not be true for all groups.
Principal, and this is an important point. Sorry, and I was a bit. Sorry, what did you say?
I mean, so it's not necessarily true for all groups such that S is
No. Here, that's why you have somehow to do it a bit like this, because you have to find for each theta, you find an ultrafilter and you get a contradiction. Okay, the ultrafilter here
but not that.
is depending on this theta, on this example.
If you find S, right, then
Yes.
you then then
Yes.
okay, yes, but we find infinite S, then is it true? But then so we can pick an ultrafilter for which the proof will work, but so it's not necessarily true for every ultrafilter such that S is element of it.
No, it's not. I mean, in general, you don't really have control, except if you say, I can find an ultrafilter extending this one, this filter. You know about filters, you don't have control on the ultrafilter. You find a nice filter, you extend it. So here is really depending. I mean, the point here is not. So we will see that those two satisfy the theory I'm talking about in the Ax-Kochen-Ershov. And the point is that it's true for any non-principal ultrafilter. But here, theta is a counterexample, so it must be true for it. Let me finish this. So what about Henselian? Let me just write something. For all bar, for all y. So when I put just this like this, it's a variable from the residue field. Okay. There exists. Okay. So for all x bar, there exists a y bar such that the rest of this px that I mentioned yesterday of y bar equals 0 implies there exists z. So here z. So this one is in the small field. This one is in. This is the residue sort. This is the value field sort. P of z equals 0, and the lift. So rest of z equals y bar. Okay, and this is a formula, a sentence theta, depending on this p, which is px. You remember what that is? It's sum of xi. So I should write it. So px is, you can plug one variable in it, from 0 to, let's say, d of xi, x to the I. You hear what I'm saying here? Yes.
You are missing the derivative.
And the derivative, yes, exactly. Thank you. And the prime of the rest. So here you have to write it formally, like sum of I x xi minus 1 equals pi of y bar non-zero. Okay, so this is telling me that the polynomials of degree d, because this is very much depending on d, is really it lifts. Maybe I'm ranging over assuming something is non-zero. But anyway, okay. Is that clear? So this is a simple zero lift, and again, this sentence is true for all of the QPs, so it will be true also for this. Right. Okay, and now what about the L?
But once
Yes.
the fact that it's Henselian has nothing to do that with the fact that the fields have characteristic 0.
Nothing to do. Yes, good point. Indeed, it's just there were two assumptions in the Ax-Kochen-Ershov. It's equi characteristic 0 and Henselian. So we check the equi characteristic 0. Okay. What about the characteristic of L? Here you have to do something. It's very small what you have to do, but this is of characteristic, right? But I'm taking the ultra product along the p's, so for the same reason as this is a characteristic 0, the L is also a characteristic 0. L is also a characteristic 0, is also 0, and for the same reason it's Henselian. What do I conclude with my Ax-Kochen-Ershov? Conclude that. Yeah. So what were the assumptions? Equi characteristic 0, Henselian. And then it was an equivalent, right? Yeah. Okay. So
Either K is not equivalent to L, or the residue fields are not equivalent.
right, but let's do it the other way. Let's do it the direct way. How are the residue field and the value groups? They are the same. Okay, so for each structure, Fp, the residue field is Fp. So the ultra product, in the ultra product Kk and Kl, they are the same. They are the same copies. You do an ultra product of Fp, and you do an ultra product of Fp. And similarly, you do an ultra product of the order group Z on both sides. Okay. Further, okay, and L is Henselian. And last, we have that K is this finite field, and so is KL. Okay, it's the same object. Gamma K is the product of Z, and so is gamma L. You wonder how this looks. It's like many copies of Z put together with the proof and the order as you expect. Lexicography of order if you wish. Okay, so now really by the Ax-Kochen-Ershov, I have that K, KL, gamma L, KKK, gamma K, KL, gamma L. All right. And how do I conclude? Conclude exactly with what I have here. As S belongs to U, by definition, S belong to U. What is S? It's a set such that this holds for every element in S. Every P in S. So again, by Walsh theorem, K, gamma K satisfies theta. Okay, because the definition by Walsh, this holds if and only if the set of primes such that it holds in here is in the ultraplex. Okay, and for the same reason, now by assumption we assume that this one did not satisfy it, so it means that it satisfies the negation. Same reason, L, KL, gamma L would not theta, and this is a contradiction to this. So it's a bit like Lefschetz. The only thing is that, I mean, the proof of Lefschetz is essentially the ultra product of the FP alg is of characteristic 0 and algebraically closed, so it's like C. The only difference is here, the only difference is that you take two ultra filters on each side and you reach complete theory. So what was the complete theory in Lefschetz that I'm talking about? Algebraically closed fields of characteristic 0. That's the limit theory of the FP alg. And here, what is the limit theory of both those families? It's the theory of Henselian valid field of equicharacteristic 0. Modulo the group and the
Sorry. So to see that the Bilbao group is this ultra product of Z, I don't need to do some verifications, right? I need to see that I have this valuation map from the product to the product, and then I see that equivalence of ultrafilter goes through, and this is right.
You're right. I mean, I'm sort of hiding some details. For instance, how do we know that the limit map is a valuation?
Even the residue field, you assume that the residue field is the algebra product of the residue fields, but it's not the same problem actually.
Yes. So there are two questions.
Mm-hmm.
First, how do I know that it's still a valid field, the product that I get? But this is, again, everything is about Walsh theorem, because being a valuation is a first order property, right? So V goes from K, from whatever this is the field sort, to the value, to the group sort. And I know that whatever times and plus mean, V of A times B is V of A plus V of B. This is true for all of them, for all my valued fields. So it will also be true in the limit structure that I get. Similarly, I mean, I could have started with this. I'm taking the ultra product of fields. I have three sorts, but I can quantify over each sort. So I can say this sort is defines a field. The two binary operations that I have in the value field sort. The plus is associative, and it has an inverse, and you can say all of this again by Walsh. When we took the ultra product of the FPs last week, Walsh tells you that it's a group of addition, multiplication, that the laws are distributive one over another. Okay.
What is the second question? You said there are two.
Yes. Okay. So hidden in there, the second question is, how do you know that the sorts are still corresponding to the same object? But it's because that's the way I can, because I can quantify in each sort. So I want to say, in a sense, that the valued field sort defines a field structure with plus times, etc., from L valued field.
This is what again.
And again, this is wash. Okay, wash tells you that for every element in this sort, I can add them together, can divide, and then it's not 0, there is 1 0. We implicitly used it last week when we said, we also used the same thing last week when we said that the ultra product of the FP is a field, because you can quantify over its structure. And that's the point. That's why the sort are disjoint in a sense, because I can quantify in each sort. So the structure, first of the structure, which is common to all those structures, will stay the same. Okay? Being a group, being a field, being a valid field. Is it clear? All right. So I'm doing everything backwards. The Ax-Kochen-Ershov will follow from another result, which is called path theorem. And we'll see what path theorem is, and we'll deduce Ax-Kochen-Ershov from path theorem, and then we'll spend the rest of the week proving path theorem. Okay. For now, what remains for us is to, okay, our next goal is to prove the Ax-Kochen-Ershov theorem.
So path theorem was known before. Is this a new proof, or
it's a more recent proof? I wouldn't say it's a new proof. It's from the 80s or the 90s.
kind of optimized proof or something like that?
In a sense, yes. It's a bit less cumbersome than the original proof, but it's not completely true. The original proof, it's really the same strategy. I'll talk about it later. It really follows the same strategy in using sort of a different ingredient, but in the end to get the same recipe. Okay, so before doing this, let's try to understand more consequences of Ax-Kochen-Ershov. More, what else does it say? So first, here we have a nice corollary. Okay, so first of all, what the proof proves, the proof yields. The proof yields that for all non-principal ultrafilter U on the set of primes, I have that the ultra product of QP, FPZ is the elementary equivalent to the ultra product of FP level T. Okay, that's really what we put in the product. And we just put that the characteristic match. Okay, corollary. I mean, I'm mentioning this because sometimes you will just, in some model theory book, you will just see that this is Ax-Kochen-Ershov. Or this is the Ax-Kochen principle, right?
Is this used in Halupczok motivic integration?
I don't think so. Another corollary is if K and L are of equicharacteristic 0, are of characteristic 0, okay, just two fields, then K is elementary equivalent to L as rings, if and only if K of double bracket T is elementary equivalent to L of double bracket T. Is that clear? Right. In particular, Q H of double bracket T has the same elementary theory as C of double bracket T. Which is not, I mean, of course, it's non-trivial, but for instance, we have QH of T is not elementary equivalent to C.
Yes,
No.
Yes, are fields now.
K and L are just fields, and this is in the language of rings. It's really because this, so if the elementary equivalent, those are the valuation rings. This is the valuation ring of this, of the residue field, sorry, of the valued field associated to this. And this is the residue field of the valued field associated to this. Yes, this is a valuation ring, right? So when I say this, equivalently, I'm saying.
So you're passing in between by the whole structure of value fields and then the.
Yes, exactly. K of T, what is it? K and Z. Okay, for me. Here's the ring. I told you yesterday, from the ring structure, you can reconstruct the field, the fraction field associated to it, and so you can reinterpret the valuation by taking the quotient, etc. That's somehow what I'm using here. So residue fields are elementary equivalent, and the value group Z in both cases, right? So
What's the last line?
in particular, QH elementary equivalent to C of QH of double bracket T, double square bracket T to C. And this is just a remark that it doesn't hold.
It's a typo, right?
Yeah, you have an extra bracket.
Ah, sorry. I mean, it's also true.
So you have to see the point.
Yes, no. I'm saying if you put a single bracket, you
Yes,
put the polynomial rings.
So single. Yeah, just did it. Yes.
Yes.
Yeah. So.
Okay. So yeah.
So it holds for series, doesn't hold for polynomial function one.
Yeah, it holds for the complete.
Now I get it.
And you also have, if you put two of them, then two indeterminate, then it's not true either. So it's really fault. Yes.
Can you, do you know how to?
Okay, so I thought about this. So it's one of those folklore things. I think you can interpret the arithmetic in here, in both actually. I think this is known. And then I guess, I'm not sure, but what I guess is that from the arithmetic, you can really say more. Yeah, so you can say, for instance, probably that the residue field
What
is.
means interpret the arithmetic?
It means that I can reconstruct from this structure, from the ring structure, the theory of this. Which seems, this ring, which seems very natural thing to do, but this is very bad in model theory. It's like the worst. It's because of all this Gödel's argument uses the fact that he can encode many expressivity in this structure or in this structure. And the whole.
But I see you can also interpret the arithmetic in the QR double bracket, no?
No.
So,
No. This is
so what is the
partial.
subtlety?
Well, how do you interpret this from this? And why can't you interpret it from this? Okay. Do I have okay, I have an argument, but you're not going to like it. Because this is tame. There are notions of tameness in model theory that we can define, which are closed under interpretation. So if you are tame, like the stability theory, model theory, one of this notion of tameness, and if you are tame, then anything interpretable in it will also be tame. Okay, and this is everything which is not tame. This is far from being tame. So because we know that this is tame, we know that this is not tame, then this cannot interpret this. Okay, I cannot.
So the corollary is that we are not stupid if we cannot come up with an elementary proof.
At least you can.
Yeah, exactly. It's really not highly non-trivial.
And if I localize, I mean, because the rings power series.
Oh, that's a very good point. Okay, so we will see. Okay, it's a good question. If you localize, but we are not.
So it's local ring, not polynomial ring, but localization of polynomial ring at ideal maximal ideal T. So that's two local rings.
But nothing happens, right?
Yeah,
They are
I'm not sure. I mean, it
Well,
will
but
not be Henselian, for instance.
Yeah, they won't be Henselian.
So okay,
But they will be local.
yeah, there will be
The
local
completions
rings.
will be this thing.
For Javier's questions, at least you can, after the end of the course of Christian, we will have quantifier elimination in these theories, and then at least you can show that Z is not definable. It's not a definable subset of any of these two rings with double parentheses. So at least you can have an idea of why this is perhaps not the full strength, but you can use quantifier elimination to prove that the integers are not really a definable subset.
Right.
What about round brackets?
Okay, so
I mean, if you do take techniques of fraction.
I think it's also known that it interprets arithmetic with round bracket for QH. Maybe that's an easier argument because for C of maybe we are digressing too much. Yeah. Essentially, we don't know much about this. Maybe it's tame, maybe it's not, but we know that. Am I saying something? Okay, I think I will stop now because I'm not completely sure. I think we know that this is not tame. Okay, I'm not sure. Let's just go on. But yes, so that was just an example. Okay, so we have this immediate corollary of Ax-Kochen-Ershov. And let me tell you a little more, to get a little more consequences of Ax-Kochen-Ershov. Let's talk about Han series. Okay, so Han series are those generalized series that we were talking about yesterday. Let me just give you a little more insight on this. So you fix a field K, any field K, and get K the field, and gamma is an ordered abelian group. Right. So we will define this, which is the generalization of Lorentz series, but for arbitrary ordered abelian group. The point of this is that if I look at this field, the value field, and the residue field is K, and the value group is gamma. So then I will have many more examples to work with. And also they are all Henselian, which is very nice. Okay, so it will be, we will have a lot of examples to work with, not only BCAM. So recall that a subset A of gamma is well ordered if for every subset B of A, B has a minimal element. And then what we define, K of T gamma is defined as the set of formal sums sigma for gamma and gamma A gamma T to the gamma, whatever that means, for let's call it A, such that the support of A, maybe two P's, which is the set of gammas in gamma such that A gamma is non-zero. This, the subset of gamma, is well ordered. You take gamma to be Z, this is exactly saying that you are stopping at some point. I mean, there is a minimal I0 such that for every j less than I0 in the integers, every coefficient is Z. Okay, so it's formal sums, okay, with well-ordered support. Then you just define. Of course, I will skip any details here, but essentially the sum gamma plus B gamma is the sum of A gamma plus B gamma, and the multiplications. I mean, you extend naturally the additive and multiplicative law from, let's say, Laurent series or polynomials. B gamma, T gamma. It's the sum from gamma equals alpha plus beta.
For multiplication, you already used the condition.
Yeah, exactly. Exactly. No, for gamma, such that beta of A gamma, A alpha, right, beta gamma. And here, I mean, okay, I can just write this. And the point is that it's an exercise. It's actually a sort of small lemma. If A is well ordered and B is well ordered, then the set of sums is again well ordered. Yes, right, this exercise. So that this again has well ordered support. Here,
And even the sum that you get is finite, because otherwise maybe you cannot even you cannot make the operation.
Yes, exactly. The number, yeah, exactly. The number of elements such that the number of different elements is finite. Exactly. Let me write this exercise. If A and B are well ordered, then A union B is well ordered. Okay. This is to define the sum. Okay, because you can have, right? A plus B is well ordered. And actually, that's for defining the sum. Sorry, I don't know what did I put this one. Really good exercise. And for each gamma, there is only a finite number of pairs alpha beta such that alpha plus beta equals gamma. Okay, that's the main point for defining this. And it's really you fix one. If there is not a finite number, then you can construct a descending chain element. Okay, and the main thing for us is really Anything more to say? Ah, yes, of course. Then I want to define a valuation on this thing. Then you define also V of term A gamma T gamma to be the minimum of the support of A gamma. Define it, and then the fact that K is a valid field. I mean, I'm doing no details here. Okay. For instance, to prove that it's a ring and it's really just checking to prove that it's a field. You need to do something. I mean, as in the Lorentz series, you have to. Yeah, there is a little argument. I detailed it in one of the exercises to really see what's it, and it uses. I mean, sort of uses the validation. The valid field such that with residue field yes, this is K, I'm sorry. Okay, maybe I can just put K of double bracket T gamma. It's a valid field with residue field small k in value group gamma. It's really value. Right, and then you have some plus it's Henselian. I think I included the proof in the notes, but it's really because it's sort of. I will talk about sort of Cauchy sequences at some point in this course. Sort of by construction, three elements has a limit. Every Cauchy, pseudo Cauchy has a limit. Henselian, right? Right, and I think it's if K is algebraically closed and gamma is divisible, implies that K of T gamma is algebraically closed. And I think, and that was a point for Immi's post yesterday, I think if K is real closed and divisible, it's also true that the resulting one is real closed.
Yeah, exactly.
Yes. And if K is real closed, you also need divisible.
Yes.
Sense. Well, one consequence of this is that you have an order on the residue field, then you can lift it to this much bigger field constructed from it. But we won't use it. That's
But there is a remark. So
yes.
gamma is not divisible.
Yeah.
You can form. You may have a minimal group that is divisible and contains it, like Q contains Z, but algebraic closure doesn't need to pass to the Ham field.
Yeah, exactly.
So the cavity.
Yeah. Okay, now I can cite another corollary. Re to Ax-Kochen, right? What is it? What's the So let gamma, let k, small k gamma be a solid field will be Henselian. Equi-characteristic 0. What can I say about K, about this structure of the K? Yeah. So I take a residual field. I have a residual field, I have a gamma. So I can construct my hand series over this. And what I will get is that K is elementary equivalent to K of T gamma. Nice. Okay, is that clear? So this has the same residual field, the same value group. It's Henselian of characteristic 0. So by Ax-Kochen-Ershov. So Ax-Kochen-Ershov is telling you that once I've fixed a K and a gamma, and I'm characteristic 0 and Henselian, I have a complete theory. And actually, if I want specific models, I can always choose a hand field. Like this. Another consequence is, if I wrote something else, what was it? Yeah, this is just a remark. I mean, nothing of here. It's very just a way of twisting the Ax-Kochen-Ershov theorem. Then it's F. Okay, so this product as a valued field, it's elementary equivalent to this is the product of a P. Okay, so it's elementary equivalent to a hand series, actually a Lorentz series over a pseudo-finite field. Whatever. Here for the same reason. So here I'm actually using here what is the value group. Here, what is it?
Ultra product.
Yes, ultra product of Z, but it's elementary equivalent to Z. Okay, so I'm using that. I had what I'm using is that the ultra product of Z is an elementary. I mean, I'm not using fully this, but it's an elementary extension of Z. So they share the same theory. Okay, the Ax-Kochen-Ershov is not only about having the same residual field, it's having the same theory of the residual field or of the value. Right. Okay. Okay. Just to finish on a bit later, let's say more. Easier considerations. Again, what's happening to my tree representation of valued fields in the case of hand series? Then it can get a bit messy because the value group can be a bit more complicated. For instance, remember I had like the position for the periodics or for FP of double bracket T, I had like I choose the first component, then the second one, etc. And this is sigma of AI, EI, for instance. Okay, so what's happening in the hand series? What if I put gamma to be dense? Like gamma is Q. Then here I no longer identifiable layers, right? I just have a bunch of dense points. But I will still use this re-representation. Although, so the main point was that if I have A and B, then the point at the intersection is at the level, what was it? What was the level of the intersection of the two branches? Yes, variation of A minus B, exactly. But this is really because here you have two different values, and before that they agree on prefix. Okay, and so here the point, which is the intersection point, might not be might not exist. Here is an example. I find it interesting, but it doesn't exist, but the representation still it makes sense. What if you take 1/2? Okay, let's say assume this is, so we are now in Q. Okay, this is 2. This is 1. This is 1 + 1 squared, etc. And 1 + 1/2 to the. What am I doing? No. Okay, you just take something which is ordered as omega. Okay.
1 + n divided by n.
Yes. Thank you. Like this one. N - 1. Is that
No, n plus.
n? Right. Okay, so it's converted to. I see the as ordered like omega plus. But what's my point here? I take a value and then a value and then a value, etc. Always the same. And then at the level 2, I take two different values. So let's say you have AI for I less than omega plus 1 and BI I less than omega plus 1. And you assume that here AI equals BI, but here A omega plus 1 is different from B omega plus 1. Okay, so I can define this sum. This is an element. A is the sum of AI TI. This is an element of, let's say, K of Q. And B is the sum AI TI, only for those values. What? BI, thank you. And then here it always agrees, but then it's like a cut. And so you see, I cannot properly draw my meeting point, but still I see that the valuation is really this layer, which is here. So it's 2. Okay, the variation of these two of the difference is 2, but I cannot draw the meeting point. But I will do as if I could draw the meeting point, the midpoint. Okay, if I were to draw a midpoint, it would be at the right place on the value. Okay, it's just a remark to convince yourself that the branching and the drawing is still meaningful in here, and it still gives a pretty nice.
Can you think of an example where the valued field is not isomorphic to the associated Hans series field in characteristic 0?
Is not isomorphic or is not?
It's not isomorphic because they are equivalent.
Right.
Not isomorphic.
Do I have an example of this? Yeah, right. Piezo series. Right, with the roots.
Yeah.
Right.
For the product of QP and FP, I think the fact that there are or not an isomorphism depends on the axioms of set theory.
Yes.
Yes. You can find axioms of set theory for which there is no isomorphism between these fields, and other axioms or other models in which these two fields are isomorphic. This is a horrible.
All right. So now let's let's focus on trying to understand this theorem of pass, from which the Ax-Kochen-Ershov theorem will follow. First, I need a little notion, which is called here, something called an angular component map. Okay, so if I have valued fields like this, I have a residue map that goes from O to the residue field, right? What's happening if I restrict my residue map to multiplicative group? And it's a group homomorphism. Multiplicative group homomorphism, and an angular component map would just be an extension of this homomorphism to the whole field K. Okay, as simple as that. KV is the valued field, and angular component or an angular component map is a map AC from K to small k, such that okay, let's take care of 0, AC of x equals 0 if and only equals 0. AC of AB equals AC of A times AC of B, and AC of A is the residue of A whenever if V of A equals 0. Okay, so I take the multiplicative group part of my residue map, and I extend it to the whole of K. It's a K star to homomorphism, and then on 0, I just send it to 0. Can you read? Right. So what are examples of this? In QP, AC of sum of AIPI, what is it? The smallest AI, which is non-zero, is A V of A. All right. I mean, you just check it. It really works well. QP and and similarly in K of double bracket T, of course, you can just do the same. Lemma of AI is A V of V of if I0 equals V of some AI. Okay, I'm taking the coefficient of the element of post index V of sigma of AI. Yeah.
Sorry, does the angular component map sends the element of the maximal ideal to 0? Because it's extending only for the units as you wrote it.
It doesn't need to.
Doesn't need to.
General, I would say.
But it cannot.
No, it doesn't. Yeah, exactly. It doesn't. Yeah. Okay, because The only thing that it's sent to 0 is 0. It's really a different map. It only coincides on the elemental variations. Okay, so apparently there are examples of valid field which does not have an angular component map. So I give a reference in the notes. Not that a bit weird, but that exists. However, in our case, you can always find, given a valid field, you can find an elementary extension in which you have an angular component. Okay, so for this, we'll use.
Is there a theory of valid fields with angular component maps?
Yes, we will. That's what path theorem is about. Okay, so in fact, it's sort of classical model theory of module or of Abelian group. Is that every Aleph1 saturated Abelian group is pure injective. You saw this last week. Let's remind what it is. So M is Aleph1 saturated. M, it's a structure in the language L. If for all, I mean, we will not use really the definition, at least in this case. We'll just use this as a black box. But for all delta set delta of X set of formulas from what was the notation? L of M, okay, with constants in M, such that the size of delta is less than Aleph1, then there exists an A in M such that delta of A, meaning that for all phi of A holds in M, for all phi in delta. Okay, for all consistent or finitely consistent delta of X set of formulas, so which means that if I take finitely many formulas in my set delta, I can find a common realization. If my set of formula is not too big, then I can actually find a realization in M. M is Aleph1 saturated. Okay, and so you have this fact, and from this, okay, so that's
Injective. Injective, I remember what is.
so pure injective means that every time you have, so let's say A is pure injective if you have a homomorphism from B to A and an extension of B, let's say in C, and if this extension is pure, then you can extend the map to A.
This extension is pure.
And this extension is pure.
What means pure?
So it means like divisible in C. Like if N, like B is equal to the set of C in C such that C to the N belongs to, okay, if C to the N belongs to B, then C of for in this situation. Okay, I just need it with inclusion. You can state it with maps. Okay, so this is being LF1 saturated, and an important fact that we use all the time, which follows from compactness, is that, I mean, and a little bit some arguments. It's like the basic tools of modular theory for all structure M and cardinal kappa. There exists an elementary extension N of M, which is kappa saturated. The saturated is really in the sense that it has enough elements to witness, it has a lot of witness of formulas and even of sets of formulas whenever this is a consistent set. For all structure M and for all cardinal kappa, there exists an elementary extension, so it satisfies the same theory. Better, it's really nicely extended, which is kappa, so N is kappa saturated. Okay, and so now I put these two things together, this together with the fact we get a lemma that K gamma developed field, there is an elementary extension K star, small K star, and gamma star. That there exists an angular component map AC K star to small K star. Okay, so I just apply the two things. I take an LF1 saturated elementary extension that K star, K star, K star, be separated elementary extension. Okay, just write AV. Then, so I want to apply this. In particular, this group is also LF1 saturated. Why? Well, it's really by definition. Now I consider any finite set of formulas in this language. In particular, it's a set of formula in the bigger language, so I have a weakness. And I already have that res goes from O star to small k. So everything is starred, okay? This is an asterisk, this is the cross of invertible elements. Notation. LF1 saturated, okay, so I want to extend this map to this group. I just have to check that this is pure. Yeah, so this group, the group is LF1 saturated. I have this homomorphism which is given. Of course, something which I'm not explicitly saying, but maybe is worth recalling for us now. I have this structure and I'm taking an elementary extension. So whatever this sort of union of sets is, in this sort it's a field. So in this sort it will be a field which contains this one. In this sort it's a field. So in this sort also it will be a field which contains this one. They will satisfy the same sentences as field, etc. Particular, the map that I have from K to gamma, from K star to gamma star is still evaluation, etc. Using this order. Okay, and so why is it pure? This in this? It's really it's the element of valuation 0, right? I mean, it's also integrally closed. I think it's easier to just say if A to N, okay, let A be in A star, then if A to the N belongs to all star times, then the valuation of A n 0 is the valuation of A n, but it's also n times the valuation of A, and I mean the torsion free group, gamma is a torsion free group from that B of A equals 0, which means that A itself belongs to all star times. So this is pure. So by the fact that this is saturated, indeed, you can extend them. This extension will be an angular component by definition. Okay, and then you extend it to this is extension of the group, not from the group, you extend it to 0 by sending 0 to. All right. So that's a cheap way of getting angular components at the cost of being in an elementary extension. But what are we trying to do? We are trying to understand the theory of a values field. So it doesn't really matter whether we work in an elementary extension or not. And that's a very important point for us. We can work in a sort of bigger model. As soon as it has the same theory, I'm still studying this theory I started. Okay. All right. So theorem of mass. Okay, maybe I will do a slight change of schedule. And we will see that tomorrow because it ends at in 10 minutes, right? Or is it?
But you started a bit later.
Okay.
So I think if you want to stay a bit more, we can shorten a little bit the break.
Okay. But I'm still gonna change a bit my schedule. Sorry for the last moment. It keeps it interesting. So I'll state the theorem of mass tomorrow. Because we have this sort of argument, let's try to see another sort of argument a bit similar, where we use model theory in a valid field, model theory and valid fields. Okay. So let me tell you about some algebraic tools that we will use very much in the proof of Ax-Kochen-Ershov on the valid field side. Okay, so pseudo convergence. All right, so let we fix a valid field KV with KV K gamma. And I mean, I don't know how much of this is known, but we will sort of need it in precise fashion, and also Immi will use it, so it's worth that we start already getting our hands dirty with this. So you all know what an ordinal is, right? So in here now, lambda will be an ordinal, something well-ordered set. Every set can be made in bijection with an ordinal, etc. So I will consider, because gamma might be very big, right? Gamma might be like Z times Z or lexicographically ordered. We are now in the realm of non-archimedean valid group. But this is why this notion will make sense. Let AI, definition, let AI for I less than lambda, for lambda an ordinal, be sequence element of K. We say that AI pseudo converges to an element A in K if there exists, let's say, an I0 less than lambda such that for all I0 less than I less than J, if I take higher and higher indexes, we have V of A minus AI, which is lower than V of A minus AJ. So we are strictly increasing when the above this bound, we are strictly increasing at the same, this function is strictly increasing as A and J. Okay, I will also say that this holds eventually. Okay, there is an element that it holds eventually. Say that AI is pseudo Cauchy. I will just write C. Yes.
Like if lambda is not a limit, then you can just take I0 to be like the previous element. No?
I mean, if lambda is yeah, let's consider lambda to be limits. I mean, you could also just say, forget about I0 and I put them all increasing, and then you say that sequence converges whenever a part of it, a final part of it is a converging sequence. Okay, so AI is pseudo Cauchy if there exists an I0. So again, I will say eventually such that for all I0, let's say G1, G2, A3 less than lambda, and we have V of A J3 minus A J2 strictly greater than V of A J2 minus A J1. Okay, let me. So this is the definition. Let's try to understand what we are really doing here. And for this, I think really it was to look at this tree representation. So I said that my tree, an element of my tree is a branch. Oh, my valid field is a branch, A. Okay, what does it mean for a sequence to converge towards A? So I have a sequence AI aj, okay, my elements are the branches of this tree. What does it mean? Assume that I is less than j. It means that the valuation of, so this point here, again, my valuation, my value group is like this. And here, what do I have? V of A minus AI. What am I asking? I'm asking for V of A minus AJ to be above this one, strictly above. Right? So so I have a sequence AJ like this, and as the index increases, I'm getting closer and closer to A.
Depends on the ordinal.
Yes. I mean, what do you mean? It depends.
The limit.
The limit, yes.
Doesn't have to be unique.
Exactly. Good point. Okay, so now let's assume that we have
Because the ordinal is very large, like the.
assume that we have a cut here. It's a good point. So assume we have a cut, like you have a copy of Z or of N here, and it goes like this. And then you have another copy. Here you have a cut, an accumulation point here. Then you could choose a sequence that just take these values. Okay, if my sequence is sort of small, yeah, then it will converge to A. The values are strictly increasing with infinity many, but it will also converge to any B which is close enough to A. So the limit, indeed, good point. If the group is in general, the limit will not be unique. Okay, so I gave you a bunch of remarks. You can prove, okay, remark, prove, can prove that convergent or pseudo convergent series is pseudo-Cauchy. So how does it look, a pseudo-Cauchy sequence? How does it look like? So you have, for instance, you fix an element AI, and then you have an element AJ, and you have an element AK. Where do you put your element AK? So you have V of AI minus J. Also, it was with G1, G2, G3. Let's assume this one is G1, and this one is G2. Then the element AG3 will be of valuation greater. Okay, so will be something like this, AG3. And then the element AG4 must be above, must keep getting smaller and smaller. And so AG4 could be like this, and etc. And sort of those seems that goes somewhere, although we already know it does not. The limit need not be unique. Okay, so pseudo-convergent is pseudo-Cauchy. I mean, it's very clear from the picture, right? AG1, AG2, AG3. Then the valuation of AG3 minus AG2 is this point, and is greater than the valuation of AG3 minus or AG2 minus AG1, which is this point. So this is so the Cauchy valuation of AG3 minus AG2 greater than AG2 minus AG1. But if you want to prove it, I mean, you have to prove it using the axiom. V of A minus AJ3 minus AJ2 you probably want to put some AJ3 minus A minus AJ3 minus AJ2 minus A, etc. It's an easy exercise. Okay. So indeed, so a pseudo-convergence sequence is pseudo-Cauchy. I mean, do you want me to do the proof of this, or is it okay? But I invite you to do the computing, because it's easy on the picture, but on the computing it's always a bit more twisted. Okay, so some other remarks. Right, you can prove that if AI converges to A, this happens if and only if. Okay. Let's assume AI converges to A, then AI converges to B. This is if and only if the valuation of A minus B is greater than the valuation is of A minus AI for all I less than lambda. So once I fix this sequence AI, and it's exactly what our what the picture shows, right? So if I have a sequence which stops here, that's A less than omega than lambda, they are all of valuation minus A below here. Then if I have some room to have other elements, and the valuation of A minus B is greater. Okay. And so this sequence in particular, you see that there is something which is constant. Once I've fixed the Cauchy sequence, then this value they are fixed. So you can just I think in general I will call them the alpha i's. Right. So if AI is a PC sequence, then I call alpha I the sequence alpha I is V of AI plus 1 minus AI. What's the point of this? What do we see on the picture? What can happen to this sequence of alpha? It's exactly the okay. So first you have to check that V of A minus AJ minus I and V of AI plus 1 minus I are the same if J is greater than or equal to I plus 1. Okay, and then what you get is that this sequence is strictly increasing. Increasing. I mean, this is really by definition. The only thing that you have to check is that, I mean, no, there is nothing to check. Yeah. There is another interesting sequence that you can associate with AI and lambda. It's easier to check. Yeah, okay. Let's assume first that it converges to A, and you define the I to be the valuation of A I. Then eventually, the sequence of beta I is either strictly increasing or constant. I'm talking really now not of V of AI minus A, but really V of AI. So you see the two cases, right? If the sequence is on the 0 branch, then the valuation of each one of those is increasing. But if I'm here, if I'm this sequence here, they all have same entries like this. Am I going to find they all have the same valuation? Yeah. So BI is either constant. Okay, eventually. So I should always say is either eventually constant or eventually increasing.
And eventually increasing, then it's equal to A alpha I, right?
To A alpha I. Yes, exactly. Exactly. Yes. Yes. Okay. Yeah, I think we can prove this, right? Can we? Right. Okay. Assume. Let's prove it.
What was the remark here? What was the remark?
The remark was, in the case when it's eventually increasing, then the beta I is even equal to alpha I.
Okay. We prove it. Let's prove it now. Okay.
Just look at the picture.
Yeah, I mean, I know. But are you confident with the picture, or do you want proof?
In the picture. So
Alpha is
Yes, alpha is this sequence. Oh. Okay, let me just do it for me to remind me that I can do this. Okay, so eventually, so assume by contradiction, just assume that V of A I greater than or equal to V of A. Okay, then eventually, okay, then if you take an element, okay, for some I greater than I0, and then if I take J greater than I, then V of A minus AJ by definition is greater than V of A minus AI. Okay, and now this by definition is greater than or equal to the minimum of those two, V of A, V of AI, which is in this case V of A. Right. Okay, so you have that V of A minus AJ, which is strictly greater than V of A. What does it mean? It means that those two have the same valuation. Okay. It implies that V of A equals V of AJ. And okay, so that's this case. So eventually, V of A is V of AJ is constant. Is it clear this sort of argument? Okay, and if not, then it's strictly increasing. Not V of AI should be greater than V of A. No, sorry, lower. So V of A, right? A minus AI. Yeah, I didn't tell you this, but if you have the valuation of the sum of two elements of different valuations, then it is the minimum. Yeah. So it's the minimum, V of AI. And then we see exactly what you said, Immi, and it's constant. It's equal to V of through those alpha. It's strictly increasing. Okay. We told that with it, if V of A is different from V of B, implies that V of A minus B or A plus B is the minimum V of A, V of B. Okay, so what's the intuition between this pseudo-Cauchy? Maybe I'll finish with this. As in the usual case for Cauchy sequences, the intuition between being Cauchy is that it behaves like it were converging, but you don't need the limit to say it, right? To have Cauchy sequences, then you can define a limit, and that's exactly what we can do. I think that's that's a lemma. Okay. AI is pseudo-Cauchy, let's say in KV, then there exists an elementary extension. Okay, let's be formal. In this, there is an elementary extension K star, small K star, gamma star, and A in K star, such that AI converges to A, pseudo converges to A in the valued field K star for the valuation V star. Okay, so for the extension of the valuation function that I had here, for the extension which is okay, and this is the same thing as we saw just before. You just have to check that if you are saturated enough, then you will have a limit. Okay, so assume that I think I need the. Okay, so AI is indexed by lambda. So lambda is given in K, and let kappa be a cardinal which is bigger than I guess the kernel of lambda plus. I just take it big enough. And consider K star, small K star gamma star a kappa saturated elementary extension. Yes, sorry. So one way, I didn't mention it, but one way of getting saturated models is actually by taking ultra-coordinate or ultra powers. I don't remember if we saw this a little bit.
No, this I didn't.
But from the construction of ultra powers, you actually you are adding many points satisfying formulas. Turns out that roughly you get a little bit of saturation by taking an ultra project.
It's a bit like the usual Cauchy compression construction.
Yes.
Model.
Exactly. Yes. Good analogy.
I mean, this is some kind of Cauchy compression. And in Cauchy compression, you take a product and you model by Cauchy
equivalence. Yes.
If you do ultra product, you do product and you model by some ultra.
Yes.
Integration. So
Yeah, that's exactly that. And I can even tell you what is the relation, I guess, that you are modeling out with. Okay, let's do it first the easy way. Okay, so maybe I can keep this. So I'm taking a kappa-saturated elementary extension, and what is the set? I want to keep I want to prove that if I want to use saturation, I want to prove that there is a point that satisfies a certain, that satisfies this, right? the point here, my point here is that satisfying this is the first order expressive. You can express it in a first order way. So what is my delta? Delta of x, in a sense, it's the set of what? Of a certain formulas. And I want this set to be such that if I take a realization of this set, then it's a limit of my sequence. Okay, so one wants to tell me what I should write. So let's keep it as a free sentence, a free variable. So yeah, but there is x such that let's see. Yes, exactly. J is bigger than x minus ai for I0 less than I less than j less than lambda. Okay, for all j such that is. Okay. Right. So why is this finitely so? Saturation, I can find the realization of this if it is finitely satisfiable. Okay. We say that it's a consistent set of formulas, or finitely consistent. What?
Because it's Cauchy.
Exactly. And so because it's Cauchy, the delta is finitely satisfiable. Why? I must take a finitely many formulas, such formulas. So let's say V of x minus AG1 greater than V of x minus, which one is AI1? And then, I take this formula, blah, 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 and another set of formulas. The last instance is x minus, let's say, AJN greater than V of x minus AIN. And I want to take a realization of this. Okay, so I took them all bigger than my bound because it's enough. So it's much easier to do it with the drawing, right? So because you have every time you have pairs, you take just the greatest, which one should be the greatest, I guess. Yeah, you take that I missing letters. I is the max of the I is. Yeah, and then I have yeah, I'm taking the biggest of this one, okay. And so you know that the G assume it's AI1, and then I just take okay. Assume that AI1 is that I1 is greater than or equal to the I case. Yeah, so because of those, then I have AI1 like this, and I have J1, which is like this. Okay, so I know that AJ. What do I know? No, that's all I know. Okay, and then the other ones are lower. Okay, so so which one do I want, what do I want to take as a witness? Because it's finite, because it's a Cauchy sequence, I know that if I take, actually I can go in both directions. Oh, okay. So I take then the I1. Okay, I guess it depends on how is J1. Now I'm lost. Ah, no, sorry. I know that this. Yeah, so my bad. Okay, so I know that J1 is greater than AI. So if I take K such that which is bigger than J, but which is lower than lambda, then the difference here with AK, the valuation of AK minus AJ1 is greater than the valuation of AK minus AI1. So I can just put AK here. Right? Sorry, I was a bit confused. Take K greater than so J1 is greater than I1, and take K greater than J1, then V of AK minus A J1 greater than V of AK minus A I1. Okay, I'm hiding something here. Formally, because it's also Cauchy sequence, it's greater than V of AJ1 minus AI1. That's formal definition, but because J1 is here above, because AK, the valuation of AK minus AJ1 is strictly greater than the valuation of AJ1 minus AI1, then the valuation of AK minus AI1 is the same as the valuation of AI1 minus AJ. This is the same V of AK minus AI1. So much easier on the picture. All right, so it's finitely satisfiable. Hence, okay, there is something I've hidden a bit that I should mention. What about those other conditions? Well, I know that the alpha I defined before, it doesn't really, I can, yeah. So, yeah, because I took the biggest one, then I can just, it's enough. A realization of this will also satisfy that those valuations are just the valuation of AK minus AJN will be the same. Okay. Okay, so I think this is enough for today. Delta is finitely satisfiable, so there exists the realization of this delta in this elementary extension. And a definition, it's a limit for the extended valuation. The limit of AI. Yeah.
So how many limits can you so you constructed one?
As many as you want. So here, look, I could, if I want, I can add to my type. I can add that they are different from many elements. I mean, I can add at least here lambda many limits in
lambda many different limits.
Right. I just need to say, okay, okay, there is a compactness argument to do well. But essentially, you are just adding, because it's kappa saturated, you can just add many inequalities. I mean, yeah, if you fix Right, fix let's say B in K, and then you can just take you can add the formula X different from B to it. Right. Okay, maybe you need to assume that you don't have already a limit in the field actually.
I think, I mean, if the actual Cauchy sequence, not just pseudo Cauchy sequence, then there's a unique limit.
Right.
Ah, wait.
No, I mean,
then you can enlarge the value, but then I can.
Ah, right. Okay. Okay. You can also. Yeah. Okay. Okay.
And then you will stop being
Then it will become again only a pseudo Cauchy sequence.
Yes.
And I mean, as soon as it's a pseudo Cauchy sequence only, I mean, the set of limits in it is an entire ball. And just by going to an elementary extension, you can make the cardinality of the ball as big as you want. I mean, really as big, I mean, any cardinality. So you have as many limits as you want, if you just want a big cardinality.
And for how many Cauchy sequence can you work at the same time?
If you do it well.
I mean,
all if you do it well. So, I mean, well, I mean, if you do it well, then you have to be a bit more intelligent. But you just take the Hahn field. Actually, we will know afterwards probably that the Hahn field is an elementary extension. I mean, we've already seen that Hahn fields are elementary equivalent. In Hahn field, every pseudo Cauchy sequence converges.
Nice.
okay. So I think.
So let me remind you where we are. So we decided to, I mean, we have our real numbers we are really interested in. We decided to take some elementary extension which contains infinitesimal element. And elementary extension means in some language, and this language, sorry, I just noticed I forgot to write. I mean, let's, for example, take the language of Euler rings together with a constant for every real number. And recall that I gave you a concrete example, namely this one, so of a possible R star. And then I told you now that in this R star, now we can express some things in a nice, intuitive, and somewhat simpler way. So, for example, 0 is a topological closure of a defined set if and only if there in this same set in R star, if you want, there are some infinitesimal elements. And then, so I proved this, and then I claimed that if you have a definable function, then this is continuous at 0, if and only if the corresponding function in R star sends every infinitesimal element to something which is infinitesimally close to f of 0. Now, I mean, we decided that proving this is an exercise. I was wondering whether I should really prove this now. I mean, the proof technique of this is similar to this one. Do you rather want to believe it, and we can look at it tomorrow during the exercise class?
I think this is wise.
Yeah.
So you can go.
Exactly. So then let's, yes. And so the few of you who didn't prove this yet have then a bit more time to prove it on their own. Okay. Yeah, I mean, I guess really, I mean, the proof technique is similar, so I hope you can just believe it. And so then let me just continue. Oh, yeah, now I just noticed I made a little list of things which I forgot to say last time. So let me first go through this list. So I should say, okay, so I hope you recall the plan is, I mean, in the reals we have some set X, some geometric set X, and we want to define a good notion of stratification of that set. I mean, that's essentially our goal. And the whole idea of this course is that this can be done in a better way if we pass to R star. And R star, so R star is, for example, this one, and you see already this, I mean, it's a valued field. And so now there are actually several possibilities to define stratifications in R
by working in something like R star. And I'm just presenting one of them. So actually, I mean, so the one I'm presenting, this is something which we did in collaboration with David Bradley Williams. There's another one which I did in collaboration with Pablo back there, which is closely related, but a little bit different. Maybe at the end I can say a bit how it's related. Anyway, so we'll stick to the one to one version. Okay, and so my plan is definitely to give you the precise definition of this stratification. I mean, actually, in some sense, the goal is to find the right definition of the stratification, and then, in principle, this needs then some proofs that this really behaves well in the way we want. I mean, I had written down 5 wishes or whatever, and we should prove that all these wishes are satisfied. But I mean, some of the proofs are horribly long, and I mean, maybe I wrote them some time ago, but I don't recall how they work. So I will at most give you a little bit of a flavor of how the proof works, but not really. And instead, I mean, my plan is rather, I mean, once we will be working in this R star, we will see that we can actually exploit this also in other ways to get a nicer, better understanding of singularities. And I will rather focus a little bit on this because, I mean, this is really fun. I mean, proofs are technical and so on. This is maybe less fun. So we'll rather do the fun stuff.
So what is the nature of the technicalities? Is model theory or is some geometry? Or...
It's model theory, combinatorics, whatever. I mean, I'll give you a little bit of flavor, so you kind of see. So, but yeah, this is a mix of model theory, geometry, and fiddling around. Yeah. Okay. And then there's one even maybe a question. So the stratifications which I will construct, they have a nice application to Poincaré series. And I'm wondering whether I should present this application. I mean, so somebody says yes. So let me ask, who has heard of Poincaré series before? Quite a lot of people. So then it might make sense that I indeed present application. So I will not be able, again, probably I will not be able to give proofs, but I will at least mention the application. So this is neat. I mean, I told you about these classical stratifications like Whitney stratifications. And so the application would not work with Whitney stratification. It only works with these ones. So this is that's a little, I don't know. Yeah. Okay, yeah, and then one other thing I wanted to say is I told you so we have the classical stratification. I told you there are the Whitney stratification, which imply homeomorphic detriviality, and then I told you there are also these Mostovsky's Lipschitz stratifications, which imply, and here actually, so here was a mistake. I said that they imply one Lipschitz detriviality. That's not true. They imply Lipschitz detriviality and not one Lipschitz. But Lipschitz. Yeah, I mean, it would be actually, it would not make sense. I mean, one Lipschitz, okay. So, and so this, and so I told you that, I mean, these ones have the disadvantage of not being exactly the thing on the right-hand side, but being something which implies the right-hand side. But actually, this one, and I told you this one is horribly complicated. This is another disadvantage. But there's another disadvantage, namely that this one is inherently non-canonical. So the statement is just, given a set X, we can find some S0 up to SD, which satisfies some algebraic conditions given here, and which then imply this here. But there is no way one can define these sets as D in a canonical way. And I mean, maybe at some point I can give you an example. So, whereas what I really want, I would really want to say, given a point of X, I want to say this point is 5 trivial, but not 6 trivial. So I want really to associate a number to a point. So I want something really canonical. And that's what we will do. I mean, we will, given a set X, we will not obtain a stratification of X, but the stratification of X, satisfying these conditions. And also these witness stratification, I mean, they are not really canonical. I mean, they can maybe be made canonical in some way. But I mean, so another advantage of our method, it will be that it is entirely canonical. So it's really, we kind of, if you want, we're defining an invariant of singularities, which is the dimension of triviality or so. Okay. Yeah, and then I wanted, so one last remark I wanted to add. So I told you, I hope I recall correctly that I mean, so the plan was somehow we have our set X, and then we want to say we have some point, we want to say X is something D-trivial near some neighborhood, and on a neighborhood of A, I mean, some say I don't know, 2 trivial near A, and our previous attempts were kind of saying, okay, let's take some neighborhood of A and say on this neighborhood, it's roughly translation invariant. And so the problem is that, I mean, this doesn't capture what we want, because what we want to say is that if I make my neighborhood smaller and smaller, then it gets closer and closer to being translation invariant. Right? Now, this is exactly, I mean, now, what I will do instead, as I think I already said it, in my non-standard world, what I will do is I will say, let's take an infinitesimal neighborhood of A, and let's say on this neighborhood is infinitesimally close to being translation invariant. Okay. Now, if we look at this, the idea in this proposition, this is saying, here on this side, I'm saying, if I take something infinitesimal, then I'm infinitesimally close to something. And this translates to the closer I get to 0, the closer my value of f is to f of 0. So this really, if I formulate this statement at the infinitesimal level, this will exactly give what I want using this kind of principle, namely that the smaller I make my neighborhood, the closer I get to translation invariant. So this is why this non-standard approach will be really useful here. And what's a little bit strange, I can already say it in advance. I mean, I know, I will tell you how to make precise what I mean by being infinitesimally close to translation invariant on an infinitesimal neighborhood. However, I do not know how to formulate the version with the smaller I make you, the more close I am to translation invariant. So usually here you really have a recipe of how to translate this statement, the corresponding statement in the reals. I mean, in settings like this. But here I'm using, I mean, it's a kind of more complicated statement to which this recipe doesn't apply. So in this part, I mean, so usually, I mean, one criticism of non-standard analysis is people say, well, anything you can do in non-standard analysis, you can always translate it back to the usual world. Why didn't you stay in the usual world? In this case, I just don't know how to formulate the same thing in the usual world. So that's a little bit strange. It will turn out that it nevertheless works as if, I mean, it would mean the right thing. So, okay. So all these were some side remarks before I really get started. Okay. So now let me go back to my planned program. So I wrote down this proposition. Let me write down a third proposition. So firstly, okay, here, I mean, I guess you will definitely believe me that, well, anyway, I didn't give a proof. but this also works in several variables. So if I take a function on r to the n, for example, and then I take, I guess this works just the same. So now I want to just give one last example, which will be, so again, we have some defined, can you read this or should I rather not write down there? Who wants me to write upstairs? Okay, nobody complains. So let me just write it for function in one variable again. And I want to say what it means that f is differentiable at 0. With, say, derivative, let me call it c. So this is equivalent to, and then I want to put a condition here. But actually, I want to use a slightly unusual definition of differentiable. Namely, there's a notion called strictly differentiable, which turns out to, on the right-hand side, give exactly what I want. So I'm slightly cheating here. But so let me quickly remind you somewhere, I'll tell you what strictly differentiable means. So the strict different, so f is, what is the definition? Strictly differentiable at 0 with differential or with derivative. C, if and only if. So how does one usually define the differential? So I look at f of x minus f of 0 divided by x minus 0, and I require that this limit here is equal to c. And it turns out that it's sometimes useful to not let only this point move, but also let this point move. So I take a second element, x prime, and I let both of them go to 0. And then I should, of course, impose that they are not equal. And I require that this slightly stronger limit still converges to c. And so I think if a function is continuously differentiable, then it's automatically strictly continuously differentiable. But if it's not continuous, then there are slight differences. And so it does make a slight difference if I'm just asking for the difference at 0. Okay, so f is strictly differentiable at 0 with derivative c. And actually here, so let me just write down, I mean, actually from this proposition, I think we can simply guess what we should write. Namely, so here instead of letting x and x prime go to 0, I will just take infinitesimals x and x prime. So what do I need to write? So for every x and x prime infinitesimal, now this is in R star, of course, with x not equal to x prime, I need to say that the difference between this here and the limit here is also infinitesimal. So f of x minus f of x prime divided by x minus x prime minus c, this is infinitesimal.
So what happens? If you substitute x prime by 0, there is a technical problem and you cannot prove differentiability.
So, okay, I mean, this proposition, I could replace x prime by 0 here, and I could remove the strictly here, and this proposition would still be fine. It's still fine, yes. It's just that this is a condition which I will later want to, which will reappear in the course. So this is the only reason. Yes, so actually let's right away look at what this condition here is saying, namely, this is, I mean, let me draw some picture here of this here. So let's say this is my graph of f, and then I take 2 points x and x prime, and so I look at f of these 2 points, and here, this here will be the slope, this quotient, so the slope of the connecting line. And this is just saying that the slope is almost equal to c. And so for x and x prime, both infinitesimal. And yes, okay, so I come back to this later. No, actually, maybe I can already tell you. So let me say already a little bit more. So I can maybe give you some examples. So if my function would be something like, how can I draw it? Whoop. I want to make a difference between differential and strictly differentiable. So this function here, if I do it correctly, this is still differentiable. So suppose that the little stairs here become smaller and smaller. This function is still differentiable because, I mean, if I take any 2 points here, the slope is roughly the right one. But if I take 2 points here, then the slope is completely wrong. So this function is not strictly differentiable. And now, geometrically, from the picture, I would say this graph here looks almost translation invariant in this direction, whereas this one somehow does not look really translation invariant in this direction. I mean, at least if I look locally, I mean, this is just my personal taste to not call this almost translation invariant, but to call this one almost translation invariant. But I mean, this is already to point you in the right direction of what we want to do later. I mean, our notion of almost translation invariant will be in such a way that this one is almost translation invariant and this one is not.
And that's why we want strictly.
And that's why I put in strictly differential. Exactly. So, and I mean, now why do it turns out that using this stricter notion of almost translation invariant, this really theory works well. I mean, so yeah. Okay. So I guess that's one thing I wanted to say on this page. Yeah, now I want to, always writing infinitesimal and so on, this it starts getting a bit messy. I now want to, from now on, consider R star as a valued field. So, sorry, this is paragraph 3, I think, after all the renumbering. Is this correct? Okay, so now if you imagine that we're in a green example, and this is already a valued field, I mean, I guess you know this, and we don't need to think about it more. I can also tell you actually, in general, you can always turn R star into a valued field. So let me quickly tell you, even if we, so we can define, so the valuation ring, I think that's how other people noted it this week. So let me say this is all those X. Now we are in this Gremlin case here. This is all those elements of R star which are finite. So finite by this I mean bounded by a real number. So i.e. there exists a real number such that the absolute value of X is at most this here. And it is easy to verify that this is a subring. So if you multiply to finite numbers, they stay finite, and so on. And then I let M be the set of infinitesimal numbers. So I don't need to recall the definition, I think. And well, clearly this is a subset of this here. And actually, this is an ideal in this ring. You can easily see if I multiply an infinitesimal number by a finite number, then it will stay infinitesimal. And actually, this is the unique maximal ideal of this ring. And what one also sees is that every element of R star either itself lies in this ring or its inverse lies in there. So this is actually a valuation subring. And so I think you have seen that if I have such a ring which satisfies this condition, so then I can define a valuation. On R star, namely by saying that well, the value group will be R star modulo. So sorry, the R star cross, again, I have the same notation problem, modulo O, the units in O, and then the valuation map V of X just sends X to the image in gamma. So X. So and then okay, so I will stick to what the others did in this workshop. So this gamma here is written additively, and then I additionally define V of 0 to be some element infinity, which I add here.
O by M divided by M will be just real numbers.
So exactly. So yes, good point. Exactly. So maybe I can write a few more things. So thanks. So for example, okay, let me write this right away. So the residue field, which is O divided by M, this is a field, and this is indeed just the real numbers. So I don't know. I mean, if you want, I can draw a picture. So this is my R star, and then so somehow I have the finite numbers here. This is the O, and then I have the infinitesimal numbers here. This is M, so in the middle I have 0, and then here maybe I have the number 5, and around the number 5 I have 5 plus or minus some infinitesimals. But then if I quotient by the infinitesimals, I am just left. So this whole thing gets sent to 5, and this one gets sent to 0. So I just get the real numbers. And what else can I say? So here now, the valuation really captures in some sense is, I should think of it as minus the order of magnitude. So V of X equal minus order of magnitude of X. So order of, how do you call, what's the opposite of magnitude? I mean, smallness in English, but I mean, it was minitude? Order of magnitude. So, right? I mean, here, I mean, recall, of course, I mean, the valuation ring afterwards, once I have my valuation, this valuation is the ring, is the set of X, which has valuation bigger or equal to 0. So negative valuation means strictly positive order of magnitude, means infinite. So 0 just means same order of magnitude as real numbers. And then this here will be the set of X, the maximal ideal, which have valuation strictly positive. So exactly the infinitesimals, if I think of this as order of magnitude. So I hope this gives you some intuition of what's happening here all the time. And actually also, I mean, the units here, these are just the ones which have order of magnitude. I mean, like the real number. I mean, normal order of magnitude if you want, so valuation 0. Okay, let me write it in some corner. And then, yeah, so and then of course, if I say valuation of A is greater than valuation of B, then it means that A has smaller order of magnitude than B. And maybe as a little side, okay, I don't know. Let me just quickly ask, are there people who are still almost not familiar with value fields? Who has almost never seen value fields? Nobody. Okay. Okay, then maybe I don't need to say much more about this. But okay, maybe one thing I do want to say is that personally, I mean, so in this case, B captures the order of magnitude. However, for me, I think it's the right intuition always in value fields to think of valuation as capturing the order of magnitude. I mean, because essentially that's what axioms are saying. I mean, if you look at the axioms, they say if you have you add two things of some order of magnitude, then the order of magnitude of the sum will be, well, whatever. I mean, anyway, it's exactly the right thing. And this, I mean, for me, this really helps a lot of having intuition of what happens in value fields. Okay. Yeah, and then now I can also define evaluated balls. At some point I will maybe need, I don't know exactly when I will need them, but let me already introduce them. So let me maybe given some A in R star and some valuation, then I will write maybe B of A, so the ball of valuative radius lambda, this will be the set of all X in R star, but the valuation of A is bigger or equal to lambda. Well, actually, I might sometimes want bigger or equal to lambda, and some other times maybe I want to have bigger than lambda. So let me just also put this into the notation. I will write either this or this.
Valuation of A minus X.
Valuation of, yeah, thanks. Yes. Valuation of, oops. Okay. Then I mean, of course, here are already some examples of valuated balls, then this one and this one. I guess I don't need to write this. But there's one thing I should say, I think, which is maybe a little bit, well, okay, one needs to get the right intuition. So if let me draw my R star, then I can define some classic, or maybe oh, okay, so sorry. Let me first do something else, then I can draw my pictures. I first want to do a version of valuation for tuples. So given some tuple in, let's say this is A1 up to AN, what is the natural definition of valuation of the tuple? Well, the best way to come up with a natural definition is think of as valuation should mean minus the order of magnitude. What's the order of magnitude of a tuple? It's the maximum of the order of magnitude of the entries, I would say. And since it's minus order of magnitude, so I should take here the minimum of the valuation of the entries. So that's the natural thing to do. And then the valuation map here on R to the n, this satisfies the usual axioms of valuation in some sense, well, at least concerning additivity, so valuation of the sum of the points is at least the minimum of the valuations and things like that. And actually, you could also write this differently if you want. I mean, since I'm taking the minimum of the valuations, and again, the valuation is kind of the wrong way around. So this is in some sense, well, it's a bit like something like a maximum norm. So if I take the maximum norm of this thing, well, if I just take a single element and I take its maximum, its absolute value, then it doesn't change the valuation of it. And so this is just equal to the valuation of the maximum norm of my element. So that's another way to think about this, that this is a kind of maximum norm. However, it turns out, actually, it's not very difficult to verify that it's also equal to the valuation of any other norm. So, for example, the usual Euclidean norm or something. And intuitively, this should be clear again if you think of this as order of magnitude. I mean, the order of magnitude of an element is its length, right? Its distance from zero. So it should also be this. So, I mean, this is an exercise if you want to verify it. So this is just to tell you that this is really the right definition. Okay, now let me give some examples of balls. So let me maybe draw them in R star square. So here I have some classical ball. So this is, say, set of x such that x that is an R square, which has norm less or equal to 1 or something like this. And then I can take a somewhat slightly smaller ball, so this would be norm less or equal to 1 over 2 or whatever. And then I can have a ball here and so on. Now these are classical balls. I mean, well, classical, they are in R star, so they're not entirely classical, but still kind of, I mean, defined like this. And now, how do valuated balls look like in this picture? Well, I can, for example, take the valuated ball, saying that the valuation is strictly positive. So, and this will be just the infinitesimal element. So I will here have a very small ball, and actually, maybe I draw it as a square because it's kind of maximum normie thingy. But I could also draw it round because it just doesn't make a difference. So this one is the set of x such that valuation of x is bigger than 0, or if you want, this is now just maximal ideal times maximal ideal. And now let's try to make this valuated ball a little bit bigger. So what, but still taking a valuated ball. So what is the next bigger valuation?
Triangle inequality is satisfied because of completeness of the theory, for example.
So the usual triangle inequality in this world holds exactly in the theory of Henselian. Yes, exactly. But yes, so yes. Okay, now I want to make my valuated ball a little bit bigger. So what is the smallest valuated ball bigger than this one? Well, obviously, I mean, I can just say I now impose only bigger or equal to 0. Right? How big is this valuated ball? Well, this is now the entire valuation ring squared. So it's all the finite elements. So this pink one, which is also our violet one, which is just a little bit bigger than this one. I mean, there's just no valuated balls in between. So I'm telling you this because at some point, the intuition, if you think of valuated balls too much like normal balls, then your intuition will fail. You should keep in mind that there are actually only very few valuated balls compared to, I mean, there are much more normal balls than valuated balls. Okay, this was just a little intuitive interlude. Okay, now I want to introduce another notion which will be useful, which is a kind of almost equal, notion of being almost equal. And by almost equal, I mean equal up to something of smaller order of magnitude. So let me just write it down, and I will right away define this for tuples. So definition, we have A and B in R star to the n. And actually, this notion here, this makes sense in any valued fields. So let me maybe write it down, or any other valued field. Then I say that A is almost equal to B, and I decided to use this here as a notation, which I just invented for this course. And so this is supposed to say, well, as I just said, the difference should be of smaller order of magnitude. So valuation of A minus B should be strictly bigger than valuation of A, for example. And now exercise. I mean, here it seems strange that I wrote valuation of A, why not valuation of B? In reality, it doesn't make a difference. I mean, you can imagine, I mean, if I draw my plane here and I have my A here, and I want the difference of A and B, so this is my A, and the difference of A and B is smaller compared to this here, then this here will have the same valuation. So this here in particular implies, maybe this is also exercise, valuation of A equal valuation of B. And now there's a small technical issue with the definition I gave you, namely, if I put 0 here and 0, well, then they would not be equivalent. I mean, this is supposed to be an equivalence relation. I mean, it is an equivalence relation, except that I should also say, I mean, if both points are equal to 0, I also call them almost equal. Okay. So
I have a question with all the things you said about the norms and the balls and everything. So the absolute value of R also extends to R star.
Yes. So the absolute value, exactly. This I should have said before, because this R star is an elementary extension. I mean, we can define the absolute value of X. It is defined as X if X is bigger or equal to 0, and minus X if X is smaller than 0. Now, I told you already that the order extends to R star, so it makes sense to use this definition in R star. And then any first order property of the absolute value which holds in R will also hold there. For example, that it's multiplicative frequency. Yes. And then also, I mean, here I wrote like this norm and so on. This also, I extend the usual definition from R to R star. Okay, so maybe to get a little bit of a feeling for this almost equal relation, which I wrote down. I lost my green. I want to use green for the example. Let's look at what it's saying in this example. So if I have some, if A is some element right now, this field here, A lambda T to the lambda, and B is a sum of B lambda T to the lambda. And actually, all these can be tuples. I mean, I consider my tuple here as the sum of tuples. And then, so now let's say that say valuation of A, suppose this is some number mu. And then if I want B to be almost equal to A, then this implies that all the coefficients before mu have to be equal, and actually all the coefficients, and the coefficient at mu also has to be equal. So maybe I can write down. So this will mean that valuation of A minus B is bigger than mu. So this means that the series of A mu minus B mu e to the mu. So all these, sorry, lambda, all these here equal 0 if lambda is smaller or equal than mu, right? And so this means that, in other words, A lambda or B lambda equal A lambda for every lambda less or equal than mu. Now recall that valuation of A is equal to mu. So I can write this A here, this lambda actually starts at mu. So now this is saying that the B will also start at mu. And so, which certainly means that valuation of B is valuation of A. And now the only condition remaining to say, now I already made sure that all these coefficients are equal for lambda less than mu. And so the only condition which I additionally need to say is that B mu is equal to A mu. So, which is exactly meaning that they have the same angular component. So since we just introduced this morning, I can use this. Well, okay, if I write this for tuples, I have to define angular components for tuple, which is not the entry-wise angular component. Okay, let me write this down in the one variable case. Otherwise, I would need to tell you what I mean by this here. In the one variable case. Okay, so this means now, so essentially being almost equal means having the same valuation and the same angular component, well, with a little twist in several variables. So I hope this gives you a bit of an intuition of this. And now I guess I should, let me just introduce a little bit of more terminology for this. Not sure how much I will use it, but it's kind of nowadays when one uses it. Some people like to use it. I'm one of these some people. So let me define RV as the quotient of R star by this equivalence relation. And then I call little RV the canonical map from, well, just the projection onto the equivalence class. And so this RV really stands for, so V is valuation, and R is for, in some sense, residue, well, in the sense that there's one residue information which is also kept by this angle, because of this angular component thing. Okay, so this is what I wrote down here. This is rather classical. Lots of people use this notation. I want to use this notation also for in my tuple world. And note that RV of a tuple is not the same as a tuple of RV. So we should put RV, this is not the Cartesian power of RV. So I put a little n here. And I put a little n here. And I guess I keep the notation for this map. So
what's the remark here?
Like,
So you define the almost, I see. Thanks.
Yeah. So maybe I can tell you why is RV in parentheses n not the same as just Cartesian power of RVn? Well, I mean, if I'm so okay, what are the equivalence classes under RV in let me just draw R star here. Here's 0. And what are the equivalence classes under this RV map or under this almost equivalence? So if I here at the number 5 and I take the infinitesimal neighborhood of 5, then all these here have this have the same RV, right? So this is one almost equal class. And another almost, I mean, here maybe I have 9 or something, and this is another almost equal class, and so on. And then now if I have my infinitesimal neighborhood of 0, this is not a single almost equal class, right? I mean, if here I take some infinitesimal element, and here's a take an infinitesimal element, then the valuative difference of these two is as big as the elements themselves. So they are not, I mean, here the classes become a lot smaller even. And then if I have very big elements, then the classes become a lot bigger. So I hope this gives a little bit of picture. And so and now if I do the same thing in R squared, then my almost equivalence classes will be lots of here, I mean, within this violet box, each equivalence class will be a box in the size of this size, right? So these are the almost equal classes. And so in particular, I have almost equal classes here. So this whole thing is one single almost equal class. Whereas the second coordinate of this point here by itself, they are not in the same almost equal class. So that's why with a parenthesis here, it's not just a Cartesian case. Okay, is this fine so far, or should I explain?
So for n equal 1, RV is equal to R. So if I take
n equal 1,
this is the angular component.
No, it's you can think of it as a pair consisting of the valuation and the angular component.
Pair consisting of valuation and constant.
Okay, is this fine? Or should I? Okay.
Yeah, the way you just define it on the line, you can also see it as the quotient of R star, the invertible elements modulo 1 plus the maximal idea.
Yes, if you want. I'm not sure whether I want to mention this because it doesn't work in, or it's complicated in higher dimensions. Okay, so okay, now let me tell you one reason. I mean, anyway, I mean, the thing to keep in mind, I think, is that this, I mean, I guess intuitively it should be clear, right? Almost equal thus means equal up to something of smaller order of magnitude. That's the main thing to keep in mind. So let me keep this. And now I want to quickly, as a small interlude, go back to my condition on strictly differentiable. Strictly differential at 0. This was equivalent to, what did I write? I had written f of x1 minus f of x2 divided x1 minus x2 minus c. This is infinitesimal. That's what I had written. Let me just write infinitesimal null means has positive valuation, right? Now, of course, I can multiply by, so what do I want to do? I can multiply by x1 minus x2 to get rid of the denominator. And then this becomes bigger than valuation of x1 minus x2. Right, I hope this is okay. And now this c, recall this c was a real number. And here I want to assume that, let's assume that c is not equal to 0 for what I want to do. And then, so if it's a real number not equal to 0, then it implies that the valuation of c is equal to 0, right? And it's a normal big number, so it has order of magnitude 0. So then this I can also write as valuation of c times x1 minus x2. And now, what did I write? I have two things, this one and this one. And I wrote that the valuation of the difference of these two things is bigger than the valuation of one of them. So now I can rewrite this as f x1 minus f of x2. This is almost equal to c times x1 minus x2 in the sense above. So this makes things nicer to write. So which part you don't understand?
So it's strictly differential at 0 is only if that valuation y is.
So okay,
yes,
I forgot the stars, but yeah. So I mean, this was our previous thing, and then, I rewrote this. No. Yeah, maybe now is a good moment for a break, I think. Okay, now let's get to some more serious stuff. So, what I call rhizometry. Okay, so recall, I mean, in the back of your mind, we still have in mind, what our final goal is. This is these stratifications. So our plan will be, we have our set X. I don't know, this was some kind of surface. And then we have some, now we will take some infinitesimal neighborhood of some point. And then on this infinitesimal neighborhood, I mean, the way I tried to define stratification yesterday was say, let's have some map alpha, which makes it, so if we want to say here it's almost translation invariant, we want to make alpha, which makes it actually translation invariant. Now we'll do it with infinitesimal neighborhoods. And now this alpha should be something which kind of changes its only infinitesimal. And well, I mean, the maps which I want to use here are the ones which I call rhizometries. So that's to explain the title. I mean, why this here? Why I have this title? So let's, for the moment, just write down a very general definition. A map alpha from some set U in R star up to the n to some other set U prime also in R star up to the n. This is called R symmetry. And maybe I want, let's already impose that it's a bijection. So a bijection is a right symmetry. If and only if. So I kind of want it to preserve translation invariance, or almost preserve translation invariance. So let me maybe draw a little picture. So maybe this is my U, and this is my U prime. So, I mean, the idea will be, I have something translation invariant here, and I want that its pre-image should be almost translation invariant. And now, what should almost translation invariant mean? If I take 2 points here and the corresponding pre-images, so if here the translation invariance is in this direction, then, well, here I took 2 points whose difference lies in this direction, then this here should still be almost in this direction. So this difference should still be almost in this direction. And how can I express this? Well, if I take the difference of these two vectors, well, okay, let me say differently. This vector should just be almost equal to this vector in the sense of this almost equal relation, which I brought. Okay, so this is my definition. So if for all A1 and A2 in U, I want that alpha of A1 minus alpha of A2, so this is the difference in the right-hand picture, is almost equal to A1 minus A2. Okay, now let's start with some remarks. So maybe the first thing is you might wonder why is it called a right symmetry. So, and the first thing is to say a right symmetry. So if alpha is a right symmetry, then in particular alpha is a radiative isometry. And so what does valuated isometry mean? I mean, if you think of valuation as a kind of distance, then it should just preserve distances. So valuated isometry just means, so valuation of alpha A1 minus alpha A2 is supposed to be valuation of A1 minus A2. Okay, and this implication here should be clear. I told you that if some two things are almost equal, then in particular they have the same valuation. So this is clear.
What's the implication of the equality of angular components? Because this only uses
So this one is stronger than just having the same valuation.
Like the equality of angular component. What's the implication?
Okay, I don't know what kind of answer you expect. I mean, I can draw a picture. So, I mean, if I would just require isometry, then I could send these 2 points to these 2 points, for example. Then, I mean, this here has the same valuation as this here. And actually, I mean, I could send this straight line to something like this here, as long as it's, well, isometry. Actually, the condition of being a valuative isometry is pretty weak, because valuation is such a rough measure. So it's much weaker. I mean, I also have a notion of isometry in a more classical sense, but in R star. I mean, using norms in R star, this would be a much stronger condition than just valuative isometry. So anyway, so maybe let me just write down recall this here, I could also have written as RV of the left-hand side is equal to RV of the right-hand side. Okay, and now you notice, I mean, now I just want to explain you the terminology. There's so there's nothing here, and there's nothing here, and there's nothing here. So if I just replace this nothing by an R here, then I should also put an R here. That's why it's called rising. So, well, it's an, I mean, so, or you can say it like this, I mean, RV knows the valuation and some one residue field digit, and rhizometry preserves valuation and one residue field digit. So this is.
So it is neither stronger nor weaker than isometry.
So isometry now in a classical sense. You mean?
Because you cannot make a rotation, so it,
yes, exactly. You're right.
It's more restrictive.
Exactly.
I think.
Exactly. Absolutely. You're absolutely right.
It's not just more. It's also not more restrictive, no.
It's also not more restrictive. No, no, exactly. So it's incomparable. Yes. Yes. So. Yeah, I should write down, and tomorrow I should do some exercises of some properties of this. So now I should say, so here I wrote U and U prime, these are for the moment arbitrary sets, but actually we will mostly be interested in just infinitesimal neighborhoods of points. And I should say, when I say infinitesimal neighborhoods, I could say an infinitesimal neighborhoods, namely some, but what I really want to take is the infinitesimal neighborhoods. So consisting of exactly all the infinitesimals.
So is a isometry an infinitesimal deformation of a translation?
That's, you can think of it as like this. I mean, you have to interpret this correctly, but this is a good way to think about it. I mean, it's not just I take a translation and I'm allowed to move each point by something.
But that would be an example.
No, I mean, because if I translate, or even if I take the identity and I move 2 points infinitesimally, for example, I could take these 2 points which are infinitesimally close to each other and move them to here. This I'm not allowed. So I have to look at it locally.
Infinitesimally has to be defined with great care.
Yes, exactly. So exactly. So if you do it properly, then it's what you're saying, and but yes, exactly. So yeah, so we will mostly be interested. So we will mostly in this when this U here is equal to the infinitesimal neighborhood of some point. So this so equal to, how should I call it? Maybe. So I could also, so let me use my ball notation, for example. The ball around A, the things infinitesimally close to A, or this is equal to A plus, so A here is in R to the n, which I consider as a subset of R star to the n. So this will be A plus maximal ideal Cartesian power, whatever you write this. Actually, maybe let me fix the notation for this. Let me write UA for the infinitesimal neighborhood of A. So I have once and for all a notation for this. Okay. And now proposition. Now let's take such a UA and let's look at its image. Alpha of UA So, okay, the alpha could send A somewhere. So alpha, I should have written alpha. Let alpha then, and the thing is that because it's an isometry, if I mean, all the other points here are infinitesimally close to A, because it's an isometry, bilated isometry, the image points will all be infinitesimally close to alpha of A. So this is contained in U alpha of A. Okay? So this is what a proof which I can just say I don't even need to write, so it doesn't deserve the word proposition maybe. So for it to deserve the word proposition, let me put an equal sign here.
Perhaps you want to say that the rhizometry is continuous.
So this is something I maybe I would have wanted to say this. Indeed, you're right. An isometry is automatically continuous, so I could have written, but you're right. This is indeed something which I wanted to say. So it's an isometry, and an isometry is continuous. So this is also nice to know, indeed.
And isn't like a strictly differentiable with constant one or something like that?
No. I mean, it kind of looks, I mean, it looks like, well, no, but it's not. I mean, the thing is, well, I mean, differentiable. I mean, this is only say, I mean, here you can still rotate your thing by some, I mean, infinitesimal. I mean, now the question is, I mean, this translation between strictly differentiable and the other condition, this was, if I have a map in the reals, then the corresponding map in the valued fields has some, I mean, so if my map alpha, if I would take a definable map in the reals, and then I turn this into a rhizometry, then something like this would be true. Okay, anyway, we will see in a second. I mean, what you were saying is kind of correct. It just needs to be said differently. We will see it in a second, the right thing to say. Anyway, let's first deal with this equal sign.
Well, that was the definition, right? I mean,
well, I mean,
assuming that C is not equal to 0, you say that the equivalence of strictly differentiable is this, how did you call it, approximately equal, right?
I mean, strictly differentiable was defined for maps in the reals.
I see. So the difference just because of Rn. I see. Okay.
And
yeah.
well, and I mean, because I mean, this is a map in R star, which does not come from a map in the reals.
Okay, I see.
That's yeah. Okay, back to the equal sign here. So I mean, intuitively, I would say something like this. This has to be true. I mean, if I mean here I have an entire valuated ball, and I send it to something. I mean, it cannot become. I mean, it shouldn't become smaller, right? Well, it turns out that this is actually wrong. And well, it's wrong if I take my R star arbitrarily. The thing is that this R star might not be complete. And if this R star is not complete, then you can omit, I mean, you can have somehow omit, I mean, make some holes. I mean, like if you have the rational numbers and you have a map from the rational numbers to the self, you can actually map the rational numbers to the rational numbers without 0, just shifting them a little bit away or something like this, because the rational numbers are not complete. But something like this you can do. So, so for this proposition, I mean, but we need this proposition for the theory to work nicely. So here, now we need to assume that we are in this specific field, or we need to impose some other condition. So let me write this down. So as an assumption, assume now that our R star is spherically complete. And I will say in a minute what this means. But let me tell you right away that the green example is spherically complete. So, for example, this one. So this is the place I told you before that at some point we have to be more careful about our star, and this is the place where we have to be more careful. Okay. So I guess I probably should prove this, right? I mean, do you want
Sure.
to? Yeah. Okay, good, good. So let me draw some pictures.
Also, we need to know what is the condition.
Well, the condition is written here. We need to know what it means. Yeah, yes, sorry, yes, indeed. Let me, I'm wondering whether I should first, yeah, maybe I can first state the condition and afterwards I will start with the proof. So, so this is a little interlude. So, definition, a valued field, I mean, maybe I write it down generally. So, valued, or should I write it for R star? Let me write it. Okay, a valued field. A valued field, which I happen to call R star, is spherically complete if and only if for every chain of nested valuated balls BI, so chain of nested balls, by this I mean i.e. BI for every I and j, either BI is contained in BJ or BJ is contained in BI. So I'm thinking of something like I have one ball, maybe B1, and then I have a smaller ball B2, and B3 and B4 and so on, but maybe I could also have some more balls in between. So anyway, that's what I'm thinking of. And the condition is simply that the intersection is not empty. For any index set I, yes. Okay, it turns out, since you're asking a question, I could, I mean, anyway, I mean, if I have twice the same ball, then I can throw one of them out. So I can assume that each of these balls all have different radiuses. So I could index them by their radius, so that I could also assume that I is a subset of the value group, if you prefer. So, I mean, this indeed, at some point, this is indeed useful to know that you don't need any cardinality, but you just need as many as the value group is big. Okay, but so this is the condition. So this is really, I mean, if you recall, I mean, when I want to define that the real numbers is complete, I can, I mean, okay, a ball in the real numbers is an interval, and saying that the real numbers is complete is if I have any nested chains of intervals, the intersection is non-empty. That's one way to say it. And one thing which is a little bit strange in this situation here is that you could have balls which become smaller and smaller, but where the radius does not go to 0, but still the intersection is empty. So this can happen in strange valued fields. And I will actually, maybe I should give you an example. So yeah, let's spend a little bit of time on valued fields. So let's say non-example. Oh, okay, now I don't call it K, my valued field maybe. So I take the field of Puiseux series. I don't know whether everybody knows the field of Puiseux series, but let me write it down. So I can take Okay, I'm working over the real numbers because I did this all the time. I could put any other field here. So I take R of t, and now I'm unhappy that I cannot take the square root of t. So I take union of this here with t to the 1/2. Then I also want other roots of t. So let's just take the union over all n of the r t over t to the 1 over n. So this thing turns out to be a nice field. And actually, this is, yesterday we were discussing, this is a real closed field. So this is even an elementary extension of my original field R. So it's, if I would not have been careful, I could take this star to be this field here. However, in this field, I can give you some strange chain of balls. So let me take, and now I have to do similar things as Christian did before. Let's see. Do I manage to do that? I take a ball. Let's start with a ball around 0. And I say length of variation bigger or equal to 1. So here I have to, so let me draw it like this. Here I have 0. And then inside this ball, I certainly have the element t, which has variation 1. So now I take a ball around t. So this is this ball. Now I take a ball around t of variation bigger or equal to 3 over 2. Okay, so now here I take a new element, t plus t to the 3 over 2. This is an element of my field of persistence, right? So, and now let's take a ball around this new element. So let me call this maybe A0, and this is A1, and this is A2. And I take the ball B around A2, and I say variation bigger or equal to, what do I want? I mean, I want to approach 2 kind of. Let's call this here. This is 2 minus 1/2. And then let's say bigger or equal to 2 minus 1 over 4. Okay, and so this will be an even smaller ball. And I guess you can imagine afterwards I set A3 to be equal to A2, so t plus t over 2 minus 1/2 plus t over 2 minus 1 over 4. And I repeat this. Okay? Each of these balls is a nice non-empty ball in my field of Puiseux series. But if I want to take something, and I note that the radius of these balls goes to variative radius 2. So still a pretty big ball. And very far from having radius 0, definitely. But if I want to take an element which lies in all of these balls, then its series has to start with. So let's call this B0, B1, B2. If A is an intersection of all the BI, then this implies that A has to be T plus T over T to 3 over 2 plus T to the 2 minus 1/4 plus 2 minus 1 over 8 plus and so on. However, this element is not an element of K, because in K I really just took the union of these things. So every element of K lies in one of those here. So every element of K has its denominator in the exponent of 2. So this is not in K. Okay, and now maybe you get an idea of why yesterday I defined Hahn series the way I defined them. I mean, or Christian also. I mean, well, Christian gratefully defined them the way I also want to have them. I mean, this is an element of the Hahn series because I mean the condition on the support of the Hahn series just has well ordered, and then the set of exponents here is well ordered, so I'm happy. So this is an element of R in Q. And so at least in this example, I see that my intersection of balls is non-empty. Okay, so let me write in this as a little proposition. And actually I can write it in complete generality if I take any field, K any field, and gamma any ordered abelian group, then the field of Hahn series over this field with that group is spherically complete. And I'm not even sure whether I mean, maybe the example explains the proof already, right? I mean, if I mean, okay, I can maybe I can tell you the proof orally, and you tell me whether you want me to write it down. So if I have a ball in this field, how does a ball in this field look like? So maybe I can write this down at least. A ball in
well ordered.
Sorry?
Is well ordered.
So the
Gamma.
The gamma is not, I mean, this is just an ordered abelian group. The group itself is not well ordered. I mean, Q is also not well ordered.
Ah, okay.
But the support of my series will be then well ordered. So a ball in this field, so let me call this maybe uppercase K, a ball evaluated in K is optimal. Actually, I just noticed I said evaluated ball. I had two versions of evaluated balls. I had the balls with bigger and those with bigger or equal in evaluation. Here, for the definition, it doesn't make a difference whether I allow both kinds of balls or only one of them, and which one of them. It just doesn't make any difference. So let me just here now use the closed evaluated balls. So it's of the form. I can always write the ball as I have some series, say a lambda t to the lambda, where lambda only goes up to a certain mu. And then from mu on, I allow arbitrary coefficients. And then so here plus, I don't know how should I write it. I write it maybe a bit sloppily. Sorry, this is now little k. This little k here. Lambda bigger or equal to mu. So maybe, I mean, this is a sloppy way, very sloppy way to write this. Maybe I should rather write t to the mu times the valuation ring of my fields, which is the series which starts at 0. So every evaluated ball looks like this. And now if I have a chain of nested balls, then the balls being nested means that these starting sequences of the series will agree on the beginnings. And then if I want to find a point intersection of all balls, I just put the parts of the series which agree together to one longer sequence. And okay, one needs to verify that the spot's well ordered, but I take a union of well ordered sets, which also form a chain, and then it is well ordered again. So essentially, I mean, it boils down to something similar to this example. Okay, do you want more details of this, or should I continue?
I would like to see a proof of the proposition.
Yeah, okay, so let's believe this now. So we believe now that that this is spherically complete. And So I hope I can erase the definition. I mean, we just recall that nested balls have non-empty intersection. I keep my picture up there. Over there. So now I think I will start by drawing a picture of giving you the intuition. So we have here, we have the let me just call it U here. So this here I will just call U, and maybe let me call this. I mean, okay, this is U prime. It was U prime over there, so I have U prime here. And okay, one inclusion, you believe me. So the only thing to prove is subjectivity, right? So subset is clear that this I told you this is just because it's evaluated isometry. It cannot send points from here too far away. So need to show subjectivity, i.e., we just suppose we are given some point B here, maybe given B in U prime, want to find an element A in U such that alpha of A equal B. There was an A here. This is not different A now. I hope this is found. Maybe this here is a yellow A, so it's a different one.
Why don't you call it C? You want to find C.
Let me call, yeah. I want to call the element here A and the one element here B. So let me. Oh, okay. Now I have this one. Okay. Let's call it C. Good. At some. Now let me first give you just a rough intuition. The intuition is as follows. So we will try to approximate the pre-image of B. And then the limits will exist by spherical completeness. So if we find a sequence, so the idea is now we start with any element C0 as the first, and we check where does C0 get sent to? Well, it gets sent to some element B0. Okay. Now, this is obviously quite far away from B, so we're not very happy. Now, where should we look for an element which gets sent closer to B? Well, here's the trick. We know that alpha is a isometry. So if we take this difference here and move the C0 by exactly this difference, so let's call this here C1. So this is now C0 plus this difference, so plus B minus B0. Now, what happens is that we know that, so C1 will, of course, be sent to something else over there. Sorry, this is B1. I call it B1. But we know that this difference here is almost equal to this difference here. So maybe this I draw this wiggly because it's only almost equal to the one over there. So which means that this difference is almost equal to this difference. So which means that B1 is pretty close to B. So I can write down maybe once. So given any C0 in U, find C1, which is a better approximation, such that V of alpha C1 minus B. So C1 is better in a sense than C0. So this is valuation is strictly bigger than valuation of alpha of C0 minus B by setting I just said C1, I define it as a rotor bump. Okay, do you want me to write down the computation for this again? I mean, it's just because alpha is the right symmetry. If you want, I can write it down. Maybe, yes, I should. Okay, so let me write it down. So indeed. So I want, so valuation, so let me write set bi is alpha of ci, just to, I mean, the way I did it up there, the picture, and then variation of b1 minus b sorry, we have valuation of this difference, let me write it down, b1 minus b0. So, okay, let me first write it down. B1 minus B0 is roughly equal to C1 minus C0, or almost equal in the sense, i.e., so variation of B1 minus B0 minus C1 minus C0 is strictly bigger to valuation of B1 minus B0. I hope this, did I want to write? I think I wanted to write this here. Now, C1 is C0 plus, so this whole thing here is equal to, so C1 is C0 plus B minus B0. So some things cancel away. So let's say this C0 cancels away. The B0 cancels away. And then I'm left with V of B1 minus B, I think. Do you agree with this?
Anyway, it's just the same as Newton's lemma we use for Hensel, just Newton approximation.
Yeah, it's if you want the Newton approximation, that's another way.
So that here we know that the coefficient is 1.
Yeah. And then valuation of B1 minus B is equal to so what did I prove? I proved that variation of B1 minus B is bigger than variation of B1 minus B0 and valuation of B1 minus, I should have written, it would have been better here to put the C's here. I guess, okay, before I get lost in it, I think exercise. I mean,
that's really
yeah, I mean,
is there any difference?
No, it's really, it is.
Whenever we do Hensel lemma, we use Newton approximation.
It is Newton approximation, absolutely.
Use completeness to go to the limit.
Yeah, I mean, so it's, I mean, one way to think about it is Newton approximation. Another way to think about it is by doing some computation. Another way to think about it is by doing my pictures. Choose your way to think about this and prove it in your way. Okay, if you want, if you don't manage to prove it until tomorrow, we can do it as an exercise together. Okay, so now we are not done, right? I mean, so what did we manage? We managed to find a better approximation. And now, of course, what do? We repeat this and we take the limit. Unfortunately, we just know that the valuation became smaller, but this doesn't mean that the valuation goes to infinity. So the sequence of points C0, C1, C2, and so on, if we repeat this,
this could be only a pseudo-Cauchy sequence. But if it's a pseudo-Cauchy sequence, then we take a pseudo limit of that thing, and then we repeat again. And we continue this, and after countably many steps, we will actually arrive at the end, or at least after as much step as the, well, if we are working here, then after countably many steps. If we work more generally, then after whatever the size of the variation group is. So that's a kind of informal way of saying this. Does somebody want a more formal way? So let me quickly say one way. So yeah, I mean,
I think you want to put the spherical completion at some moment.
Well, I just did in sorry, I'm sorry. I was saying we take if the valuation does not go to infinity, then it's a pseudo-Cauchy sequence, and we take a pseudo limit of that.
This is where.
And the existence of the pseudo limit follows from spherical completeness. So because I mean if a pseudo-Cauchy sequence, then each term of the sequence gives me some ball, and the limit, being a limit just means being an intersection of nested balls. So spherically complete. Maybe I could also have written this spherically complete. So maybe call it lemma. This is equivalent to every pseudo-Cauchy sequence converges. Okay, if you are unhappy about my vague arguments right now, I can also make it precise without all this hand waving and using directly spherically complete.
What you just said that these arguments about that you need quantum minimalist step.
Yeah, exactly. This was very hand waving.
Yeah,
So, okay.
I had no idea. I had no intuition. Was
yeah. No. Okay. So let me make this pretty precise. I mean, this was maybe too late. So, I mean, intuitively, I like to think of this as we construct the sequence and we approach the point. We get better and better approximations of the point we're looking for. But formally, the better way to formulate it is to do a proof by contradiction. So we assume that we have some sequence of approximations of our pre-image which cannot be extended. And then we show that this gives either then it already converges really to the thing, or we get a contradiction. So let me write this more formally. So choose a maximal sequence C lambda. And now here I called my C's here C0, C1. I indexed them just by some natural number. Here I will directly index them by some elements of the value group, which specify how good my C lambda already is. So lambda runs over a subset S of the value group to the maximal sequence like this with the following property. Say valuation of say okay, I define B lambda to be alpha of C lambda as in my picture over there, and then I want that V of B lambda minus B is equal to lambda. Okay, and when I say choose a, I choose a maximum, actually I'm in particular interested in whether I can find some C's here with very big lambda. Okay, and now I claim that, claim S is unbounded in the value group. So the value group, I mean, actually my proof here, I could write Q here for the value group, but the proof works for arbitrary value groups. So S is unbounded in the value group. And if it is unbounded in the value group, then this means this we get an actually converging sequence. So it converted to some C, and it's not difficult to verify that alpha of C is equal to B. Okay. Now, suppose it's not unbounded. Then there are two cases. Either it has a maximum.
You're using kind of Hausdorff.
Sorry?
You're using a kind of Hausdorff because you compute the limit and.
Yeah, well, I mean, okay, yeah, maybe I'm implicitly using Hausdorff, yes, but I mean, values are Hausdorff. So
It is.
yeah, I mean, any two different elements have a valuation which is not infinity. So this is Hausdorff indeed. Actually, in a minute we will compute limits of pseudo-Cauchy sequences, and this is actually a special case of that. So we will make this more precise in a minute. Oh, but okay, case one, S has a maximum, which I call mu. Maybe.
In the previous lecture, we constructed elementary extensions
Yes.
with as many limits as we want for the same sequence. So in particular, they are not spherically completed.
No, the thing is that here, in this case, yes, S is unbounded in gamma. And unbound means that the variation goes to infinity. And then the intersection of the balls will be just a point. And then there's only one limit.
This is what didn't happen.
This is what didn't happen last. Exactly. Okay, actually, maybe I should not even have written this claim here. I will. This is probably just creating more confusion. Let me first. Yeah. This one. Case one. S has a maximum mu. So this means so we have some elements C mu. So i.e. have some C mu. Oh, okay. Which has this B mu, which I call alpha, which is alpha of C mu, and variation of this is equal to mu. But now I can apply my construction, which I have here, to this point C mu, and I get a better approximation. So using construction on the right, find some C prime with variation of alpha of C prime minus B bigger than mu. So actually, my sequence was not maximal. So I can append C prime to my sequence and for contradiction. So the sequence cannot have a maximum. Okay? If it doesn't have a maximum, then then I look at the balls that B lambda, so for lambda, for each element of the sequence, now I construct the corresponding ball. So for lambda in S, with B lambda to be the ball around C lambda of radius lambda. Okay. And then I claim those balls form a nested chain. So this, I guess, I need to verify. A bit of a computation, I think, but it's since time is getting short, let me for the moment, let's just say let me for the moment say exercise. If there's time left in 3 minutes, I will show you how to do this. But I mean, this is really just computation. Then, now I use spherical completeness, so the intersection is non-empty. By spherical completeness, the intersection is non-empty. And actually, I should have written something else here. This B lambda, maybe this makes it clearer that it's a nested chain of balls. I could also say, I mean, if I know that this C lambda is of quality lambda, then any other point which has distance lambda from C lambda is also of quality at least lambda. So meaning that this ball, I can also write, this will be actually, it will be exactly the set of those C where valuation of alpha of C minus my desired point B is bigger or equal to lambda. Okay, so choose now my intersection is non-empty, so choose T prime in that intersection. Then using this definition of my ball says that the image of C prime will be closer to B than any lambda in S, or at least as close. So, but then since my S is unbounded, it will be even closer. So let me write this down. Then valuation of alpha of C prime minus B is bigger or equal to lambda for every lambda in S. So now this can mean two things. So either, yeah, so, and now let's see if so if alpha of C prime is equal to B, then we are happy. Okay. Otherwise, we can extend our, actually we again found that our set S was not maximum. So extend S using this C prime. So because, I mean, this C prime, so its valuation, yeah, wrote its valuation is bigger or equal to lambda, but since there's another element in, I mean, since S has no upper bound, the valuation, so this here is actually, well, it's bigger than all of them, so it's not, yeah, it's not in this. So exactly. So we saw that in either case, I mean, either we get a contradiction to the maximality of S, or we actually found the desired limits.
Sorry, what you want to say maybe is that this kind of extension you could finish in finishes. There is an upper bound like the cardinality of value group, right?
Yes, I mean, the way I formulate it now is now just by contradiction, so I don't even need to think about cardinalities anymore.
Okay.
I mean, the way I've been thinking about it before by constructing it, then I need to think about cardinalities. And the one can then indeed make it precise using the cardinality of the value group and things like that. But yeah. Yes, so that's why we need spherically complete, and on my time.